It's chemistry, physical chemistry, with accent on quantum properties, because you want to predict observables for realistic experiments, right? And you are powerful experts in quantum theory and scientific programming right now. So you can predict the future by evolution operator, by eigenfunction expansion, and by Heisenberg equation of motion, right? And you can apply it to electron in free space and in box of any size and shape. And later, we agree, you were not protesting, kind of we found common, something common, but small atoms can vibrate away from their equilibrium position in molecules. And these vibrations may carry some quantum features as well, right? It is where we are. And then we may want to practice our overall procedure of, well, there will, I shouldn't hide it, I should have clear it in my mind. So we will try to apply whatever we do to infrared spectroscopy. And the practical benefits directly to infrared spectroscopy when something is vibrating is not as intriguing to justify like 2 weeks of lecturing for quantum theory. It's somewhat relatively simple. Why are we going to, we already invested some time into this quantized oscillations, and we are going to invest even more time. What are our motivation? Assuming that majority of audience here are whatever, it doesn't, it even appearance of young enhances my statement that majority are chemists. So if we here are chemists, why should we spend time on these quantized oscillations? Is there anything beyond the infrared spectroscopy where we need oscillations and when they need to be quantized? We already discussed, and I don't know, it could be potentially a good question for some quizzes, but yeah, I doubt we should minimize this formal things. Which systems exhibit vibrations in chemistry and generally in science and in nature? So atoms, then Christian will prompt his favorite metal objects with plasma resonance, when collective motion of electrons. Also collective motion of electrons in the LC circuit, induction / capacitance. Well, boring examples of mass on a spring, but then there are no quantum properties. It is so big, so that all constants are bigger compared to Planck constant. Well, we, in about a month from now, not immediately, so we will finish, share the plans, and I probably will update the list. So the course doesn't end here. There will be like 40 meetings total. When we will be done with quantized oscillations, we have to spend some time on spin and angular momentum, which is standard things. You may have seen it in other courses, like maybe in the inorganic. But then we may merge together quantized vibrations and electronic degrees of freedom, which can be due to spatial confinement or due to spin degree of freedom or something else. And we will be able to have a new glance on electron transfer problems. Or electron transfer is meaning that electron is transferring, and those before it has been transferred from one part of a molecule to another one, they are going to undergo drastically different potential energy surfaces, drastically different law of motion, drastically different force constants that drive their vibration. So it will be kind of, in simplest case, a dimer, 2 pair of atoms. In more complicated is something like 200 atoms. But their primarily nuclear mode of vibration will have one frequency if there has been no charge transfer, frequency 1. And then upon charge is transferred, it starts moving with different frequency and different spatial arrangement. Sometimes it is so drastically different that it is even not conservative. It will be charge transfer facilitated desorption, dissociation. And when we are targeting this far going goals, we may want to accumulate more and more muscles in describing quantized vibrations. So it is practical benefit for physical chemistry. Even more far-reaching goal, if you do not have charge transfer, you have a molecule, a chromophore that shines light or absorbs light. Also, when you excite it from ground to excited state, the quantity, the style of vibration does change. The equilibrium position change, frequency change, potential energy surfaces are changing. And this is critically important part of UV spectroscopy. If you are exposed to characterization of organic materials, you do know that even simple molecules, they have not a linear spikes, they have very distributed spectrum. And you may have heard the effect of Stokes shift, that even if you have two levels, absorption and emission spectra have very different shapes. So nuclear motion is very much guilty in this, quantized nuclear motion. So it's just a little motivation why we should spend time. So enough motivations. Good? I don't remember. You should. Eventually. And of course it doesn't hurt, well, it does hurt to develop mathematical muscles and learn how to describe it in precise way, but we need to pass through some painful steps in being able to describe these quantized motions in more quantitative rather than qualitative language. It will be painful for me as well, especially if I had just 15 minutes for preparing notes, meaning that I need to derive something on the fly. Any objections in this general paradigm, in this vision? So, I do not want to do any, I'm trying to avoid any exams or quizzes, but you may just memorize on the back of your thoughts. Possible systems where quantized vibrations do play a role. Even if it doesn't come into any question for grade, it can be helpful for your future. So those were general considerations. More practical. Of course, I'm always lying to you and telling that we're done with theory and we go into applications. But as you see, we accumulate more and more methods. And but in oversimplified way, at least in the wish list, we want to have a just limited list of methods and then apply it to new systems. So if we want to predict, and oscillations are time dependent. If it is time independent, you just find frequency and that's it. So we may want to predict some observable related to time dependence for quantized oscillation. But before we go to the time domain, which is indeed most interesting, we need to learn properties of static properties of quantized vibrations, which means time-independent Schrödinger equation, which goes in a standard way. We set up Hamiltonian, we plug it into equation, and find set of functions and eigenenergies. So it is what we started to do last time. And if today will be a lucky star for me and for you, last time we did ground state, and if it will be a lucky day, we will get to the first excited state, the second eigenstate of the quantized oscillator. So it will be criterion of success. But before this, I want to present you my main achievement. So here are your votes, and here how I summarize them. So please, if you are completely happy with everything, just record it and start preparing. If you want to complain, you can do it now, or send me a personal email. So I do see several, well, let me introduce what is going on. So some of you have selected more than one subject, and we need to cover all of them. So therefore, instead of 25 subjects, now we have down to about 12. You have a mostly condensed 2, 3, or even 4 subjects merged into one. So London selected to tell about alternative modeling of electron dynamics, and then he mentioned that he wants to tell something about storing dynamics in form of YouTube movies. Alternative dynamics by YouTube movies. No protest? No? Okay. I was worrying mostly about this. For the rest, you will see that some of the presenters do have a merge of practical, I wouldn't say theoretical, but a question about protocol of running the code, and merged with some simple applied question. Otherwise, we wouldn't be able to cover all things. So once again, and some people didn't attend the session when we were doing votes, and if you are in the room, I see you're not, or if you are watching this recording, it's still not late to sign up. It is not required, but amount of credit for this would be especially helpful for the final grade.
Some have dropped by now.
Huh?
Like some of these guys had a drop by now.
I don't know. I need to reset my campus connection password.
Has it been 90 days?
I wasn't able to log in, and it was like 15 minutes before the meeting, so I was rushing to put this slide and then quickly summarize something for actual lecture material. Not enough time to call the support or whatever to change the password. Okay. But still, even if these lucky guys do not sign up for their presentations, we'll try to keep the format of being brief. Even if we use 4 minutes instead of 3, then we will be over time. It's better to have some time to walk into the stage, to return, maybe to ask pleasant or maybe not pleasant questions. And the main idea is that an individual becomes expert in one subject and then shares his or her personal experience to others. So that because and then it will be more efficient way of getting through this material. If you still have doubts, if this has any value to you except just doing as everyone else is doing, there will be mini research projects that will be based on skills that you present right now with the scope. And all presentations up to now, including this one, were freewheel, and research project will be not freewheel, it will be mandatory. If you didn't attend preparation steps, I don't care, but project will be part of the course. So you help yourself through this presentation. Okay. If you don't feel comfortable, well, if there are no objections, I'm happy. If there are some objections that you want to communicate in private, I'm staying open. So I hope everyone is happy, but if someone is not, we can reshuffle the material to make everyone perfectly happy. Okay, so where did we stop last time? This was 2 meetings ago. This one's 1 meeting ago. And to my understanding, this number 2 was wrong. There should be no square. And I'm very doubting about this square. So it is my homework for our next meeting to and you also can just go into Wikipedia and check if in which power frequency coming into the power of the ground state of harmonic oscillator. By dimensions, power of exponential should be always no dimension, right? And we can figure it out together right now. Like H bar is energy times time. M omega square R square is energy. So right now we do have energy divided by energy square times time square, which looks wrong, right? I feel a little bit better that I caught myself on error earlier than you did. But you are very welcome to follow and try to catch. It's okay. So, if we, right now I'm doing cheesy things without first principles derivations, just checking what can we do to fix the dimension. So if you remove square here, it will be e to the e times t. And dimension of frequency is 1 divided by time, right? So if we remove frequency from here, it will be equivalent to multiplying by time, right? So if we just remove square sign here and square here, then the dimension will be e times t divided by e times t will be no dimensional. First, but the general analysis about comparison of Planck constant to the mass and frequency stays active. So I was not lying in this qualitative analysis. So if system is so massive, or if the frequency is very high, then denominator grows and width of wave packet becomes negligible, which means it is a classical particle with certain position. So this is the equation that we decided not to solve. We try to take a bypass, and later on we can plug in the eigenstates that we find into this equation and check if they will give the right solution. And of course, at any point we can just open Wikipedia or any textbook. It is not a hidden information. Check what should be going on. So then, I don't want to be spending too much time in books. So by now we do have ground state of this quantized vibration. Do you see any similarities to the another bound state that you know by now? With other similarities with ground state of particle in the box? Well, there's one peak, and if you are far enough from center, it's close to zero. So, of course, mathematically it's very different, but qualitatively it's very similar thing. Now, if someone would hire us as a brilliant mathematicians to solve this problem for money, probably it is not enough to get the full payment, because it is not yet an answer, since it doesn't have the normalization constant in exact radicals in mathematical sense. So it's just a variable. Who cares about normalization? Why do we need it? Should we just be rigorous to ourselves and torture ourselves with more exercises, or there is a necessity for this normalization? Any ideas? Who needs normalization?
Anybody that wants to talk about the probability of something happening?
Okay. Probability lovers need normalization. Who else need normalization? What is the logic? So again, we want to predict outcome of experiments. We want observables, right? Which we are getting as expectation value, star, operator, wave function, and then we integrate over whatever variable are, right? If each of these wave functions are multiplied by 10, then answer will be 100 times bigger. So if the non-normalized wave function is used to generate observable, it will be, by definition, a wrong answer. So normalization is needed to predict observable in the right way, in the exact way. And if you're not sure that your wave function is normalized, then you can put normalization right in this equation. Integral psi star psi dx. So normalization is needed if we ever plan to find observables. Make sense? So it is not just a free will to torture young brains. So we need to find this n constant. And another thing, if you are going on our path, is to find first excited state, which will be just applying the equation operator to the ground state. If you believe that this philosophical idea that we kind of accepted is working. Okay. It is why I'm so stressed without undergraduate course and why I like graduate courses. Because if it is scheduled as a 2-hour meeting, one can freely make an introduction for 40 minutes and then slowly start to direct things. And now it looks like when I'm done with introduction in my favorite style, the time is over. So we are getting the weather operator for harmonic oscillator. It is our navigation stuff. So take this square root of fundamental constants out of brackets and have m omega in front of r and nothing in front of p. Again, it was training of a memory. In last meeting, we got the factors in front of p and r by solving system of algebraic equations to match our requirements. So there is a chance to scroll back and get exact answers. Normalization. So phi, yes, it is what I wanted to see. R squared, 1 omega to h bar. And we, in order to find m, we need to just multiply it by itself and make sure that it is equal 1. So if we solve this, if we do this equation, we can solve for the n. Right? So it shouldn't be too challenging, even for me. So we get normalization squared, and then square of exponential or any power is just multiplying the power by factor 2, right? So I'm going to remove this 2. So minus 1 omega h bar r squared d dr. How do we take such integrals? What do we do? Well, it's trivial. We know it is Gaussian integral, our favorite. We know that it should be square root of pi. Can we immediately say, oh yeah, sure, square root of pi? Or no?
There's some constants that you got to multiply by.
Yes. Which constants? What is the logic? How do you get them?
I want to say it's like.
Well, from the top of the head, it will be like square root of h bar over m omega.
Yeah.
Right? But how do we get it? We can redefine the power of exponential as minus u squared, and then modify the integration variable in such way that it will correspond to this u squared. So it will be n square integral. So m omega over h bar r squared equals u squared, which means u is square root of m omega divided by h bar times r, and then dr will be du with a factor square root of inverse of this h bar over m omega, right? So if you do this substitution, if you put this factor in front, then the integral will be square root of pi. Here steps are skipped. And then we have this stuff times n squared times square root of pi equals 1. So this is the equation that we need to solve for n squared, right? So we keep n squared at one side, put everything else at other side, and take square root. So we have already one square root here, and if we solve for n, we will have one more square root, which means the power 1/4. So from here, normalization constant will be this square root of m omega divided by h bar times pi. So my goals are not fulfilled because therefore looking forward to see you on Wednesday.